All right, so welcome back. We'll get started for today. So last two lectures we've been looking at the transport layer and the plan. So last time, well, I guess maybe 3 lectures back we got started on transport layer, and we were talking about the basic services provided by transport layers such as multiplexing and demultiplexing, and then we talked about how we can use sockets to do that, and then we talked about UDP and the services that UDP provides. And last time we got started on reliable principles of reliable data transfer, and then we also got started on TCP, right? So the plan for today is that we will finish our discussion on TCP. So previously, I think on Friday, we talked about segment structure. So today we'll talk about reliable data transfer, flow control, congestion, and connection management, and then congestion control in TCP. Just a quick recap of what we did on Friday. We were talking about reliable data transfer, and in this case, we got started with the basic idea about how we can provide reliability. And the idea was that, so basic idea is when you send a piece of data, we wait for an acknowledgement from the other side. If we get that acknowledgement, then we think that everything is good. And otherwise, we wait for a period of time, there's a timeout, and then we retransmit. Right? So this was the basic idea, and then we also saw that we actually need the sequence numbers for both the packets as well as the acknowledgements for this to work. And last time we talked about the performance of this basic stop and wait protocol, and we saw that the performance in terms of the utilization of the link may not be very good with pure stop and wait. So one way of avoiding that is by allowing for pipelining. And here you're allowed to send multiple packets at a time before you need to wait for an acknowledgement. So you can send a window of packets or n packets, and then you wait for an acknowledgement. Once you get an acknowledgement, now you can transmit newer packets. And while this was the basic idea, we saw that there are two general classes of these pipeline protocols, go back N and selective repeat. In both cases, we allow you to send up to, let's say, N packets before you need to wait for an acknowledgement, but there's some differences in the way they're implemented. In go back N, we use cumulative acknowledgements, and the receiver only cares about packets that are the next in sequence coming in. And at the sending side, we send, let's say, a window of packets, and I have a single timer associated with the oldest packet. And in case there's a timeout, I retransmit everything in that window. In the case of selective repeat, at the receiver side also, now I have a window which is larger than 1. And if out of sequence packets come in, I keep them and I send acknowledgements individually, one for every packet. And there's no cumulative acknowledgements anymore. Every acknowledgement has its own sequence number. And in this case, every packet also has, every time I send a packet, I start a new timer. And if there's a timeout, I only retransmit that specific single packet, not everything. Okay? So these are things we saw last time. And then we got started on TCP. We saw that there are various properties with TCP. It's reliable, in-order delivery, bidirectional, connection-oriented, and all those things. And we also looked at various parts of the TCP. We looked at TCP packet structure. And then we talked about sequence numbers and acknowledgement numbers that we put in. And we went through this example. All right. So I think, if I remember right, this is where we stopped. So today we'll start talking about the reliable data transfer in TCP. And previously we have seen that one way of building in reliability is through the use of timeouts and so on. And we'll see that TCP actually uses that, but also to improve the performance, it uses a second mechanism to detect attacks and then retransmit packets. So let's start over. So what TCP does is, it sits below the application and above the network layer, right? The network layer, or the IP protocol, it's unreliable. It does not give you any. So, all right. It does not give you any guarantees. So if you give any data to the network layer, it will try its best. But then, it will not recover any losses for you. Each packet will be treated independently. They can go via different paths and so on. So what TCP says is, doesn't matter. Let the other layers do whatever they want. On my own, I will give you reliability. So if there are any packet losses, I will figure that out. And going back to our discussion previously on, stop and wait and pipeline, what does TCP do? Of course, we saw that stop and wait is not so good. So TCP actually uses a pipeline protocol. Now, in the case of pipeline protocol, the last two things we have seen, go back N and selective repeat, the N is fixed. So if I say my window is 5 packets, I send 5 packets and then I can wait. TCP also does pipeline, but the size of the pipeline varies over time. And the exact size is determined by TCP's congestion control algorithm. And today we will see how TCP's congestion control algorithm works and how it updates the value of the window dynamically. TCP also uses cumulative acknowledgements, just like your go back N. But TCP is not exactly equal to go back N. There are some differences, and there are some elements of selective repeat in there. And go back N, there was a single timer, right, associated with the oldest packet. TCP again does the same thing. It can send a pipeline of packets. It can send 20 packets, let's say, but there'll be only one timer. Right. And the way it detects losses are through two things. One is through timeouts, that's we understand. Another thing is through when it receives duplicate acknowledgements, and this is something we will spend a bit of time. Okay? But let's get started with the basic recovery mechanism of TCP and see how that goes. Let's look at the TCP sender in a little bit more detail, right? How does the sender behave? So in general, the sender has 3 things it does, or it reacts to 3 events. One is when it receives acknowledgements, once when there is a timeout, and once when this application gives it data. So let's see, when application gives TCP data, what does it do? So the application has given, I'm TCP, I'm transport layer. Application has given me some new data to be sent. What do? First, I create a segment or a packet. And then I insert the correct sequence number in there. What is the sequence number? I see how many bytes have I sent so far. What is the first byte of this new data? Maybe it's the 700th byte. So then the sequence number will be 700. This is something we saw last time. So I will give it the right sequence number. And then I will check. Have I all changed this guy? I think. So I check, is there a timer already running for some packet that I have sent earlier and I have not received the acknowledgement? If so, fine. I only need one timer. One timer is already running. I don't need to worry about it. If there's a timer not running, that means no data is out there now. I should send this packet and start a new timer. Right? So this part is fine. What if there's a timeout event? Right? Let's say I'm the sender. I had sent some packets. I'm waiting for the acknowledgements. Acknowledged didn't come, but the timer has expired. In the case of a timeout, I will retransmit the packet and I will restart the timer. Now, in the case of TCP, so far what we have seen is things look very much like go back N, right? A single timer, pipeline and so on. But in the case of TCP, I only retransmit the oldest packet, not everything in the window. So in that sense, it's somewhat like selective repeat. Okay? I may have 5 packets that I've sent so far, and there's a timeout. I don't retransmit all the 5. I only transmit the first packet in the window. Okay? So that's something TCP does. And then it'll retransmit. And when you receive an acknowledgement, I check what kind of acknowledgement is this. If it is acknowledging data that has not been acknowledged before, I will, for example, shift my window and so on, and I will restart a new timer because the oldest packet has been acknowledged. Okay? So let's take an example and see how this works, and I think it'll be clearer with these examples of TCP retransmission. Right? So first, let's take a very simple case where the acknowledgement is lost. Okay? So let's say the sender sends a packet, and the sequence number is 92. That means so far I have sent 91 bytes. They have been acknowledged. So this is starting at 92, and it has 8 bytes. So that means it has bytes number 92, 93, 94, 95, 96, 97, 98, 99. Okay, those are the 8 bytes in this packet. So the packet was received correctly. So the receiver has now received up to byte number 99. So now it sends an acknowledgement. And you remember from last time, when TCP sends an acknowledgement, it doesn't say I have received up to 99. It basically says 100, saying I have received till 99, give me 100. Right? So when the acknowledgement goes out, it says 100. The acknowledgement number, that field in the packet will say 100. But now, this acknowledgement is lost in the network. So there's a timeout at some point, and at the time, the same packet will be retransmitted. Sequence number is still 92, and I have 8 bytes of data. And when the receiver gets this, it again resends the same acknowledgement, saying, I got another packet, but this only has data from byte number 92 to 99, so give me 100 now. So this is the simplest possible case of timeout and retransmission. Let's look at some more maybe interesting cases. In this case, we have a premature timeout, right? So timeout is, I set up a timer, and then the timer expired, I didn't get an ACK. How do I know what that value of that timer should be? Should it be 1 second? Should it be 500 milliseconds? So in general, TCP will try to make a guess. Sometimes the guess works, sometimes it doesn't work. So let's say we made a guess, and the guess was too small. Sorry, the guess was too large. I picked a very large value. No, I said premature, so it should be small. Anyway, so I send the same packet, let's say 92, sequence number 92. It has 8 bytes of data. And then this is the value of the timer that has been chosen. And let's say I made a mistake. How much should I wait? I should at least wait for the packet to reach the other side, and the acknowledgement should be coming back. I should wait for at least the round trip time. But let's say I made a mistake. I chose something smaller. Okay? So in this case, I chose something smaller. So the acknowledgement was actually sent, and it was received, but it was received after the timeout expires. So what would happen? While I'm waiting for the acknowledgement to come back, the timeout would happen. And in this case, let's make it a bit more interesting. Let's say I had, in that example, I sent only 1 packet. Let's say in this case, I can send 2 packets. My window is large, right? So let's say I also sent a second packet. And in this case, the second packet has 20 bytes of data. The first packet started at 92, had 8 bytes. So it consumed sequence numbers from 92 to 9. It had bytes from 92 to 99. So the second packet, the sequence number is 100 because that's the position of the first byte in that packet. And it has 20 bytes of data. So basically it goes from 100, 101, 102, all the way up to 119. So if the receiver gets this packet correctly, the acknowledgement should say, give me 120. Right? And that's what it shows. It says, give me 120 now. So both the packets were received by the receiver, acknowledgements were sent, but before the acknowledgements could come here, we have a timeout. So at the sender side, okay, and another thing I'm showing here is, now when the first acknowledgement would come, the sender's window will shift to 100. And when the second acknowledgement comes, the sender's window will move to 120. That's what that one says. Okay? But anyway, let's come to the important part where now we have a timeout. So when the timeout happens, I have shown these acknowledgements before, but what has happened is I have sent 2 packets. I'm waiting, nothing has come. There's a timeout here. So I'm going to retransmit a packet. And when I retransmit the packet, I only retransmit one, not both. Okay, that's what TCP is. It will retransmit only one. And it will retransmit the oldest one, and the sequence number there is still 92, and it has 8 bytes of packets. After some time, when the 2 acknowledgements come, of course it knows it has received things, it will move along. What about the receiver? The receiver, as far as the receiver is concerned, this is duplicate data. It has already seen bytes number 92, 93, up to 99. So receiver doesn't care. It's going to throw away that packet, but it has to send an acknowledgement. In response to this, when the sender sends back an acknowledgement, it checks, how much have I received so far correctly? So far, I have received up to 119, right, from the second packet up there. So when the receiver goes back, for this, the acknowledgement still says 120, not 100, right? Just because acknowledgements in TCP are cumulative. So far, how much I have received? Earlier, I have received 100 to 119. So the acknowledgement will say 120. Any questions? Okay. So let's take a look at a third example. And this one basically shows you about cumulative acknowledgements. So let's say I again send my first packet, which is 8 bytes long, starts at 92. And let's say this is a pretty large timeout value I have chosen. The acknowledgement was sent, and that acknowledgement got lost. Right? But just like in the previous example, I was allowed to send 2 packets. Let's say my window was large enough. So I send a second packet. And this one has, again, 20 bytes starting at 100. So it goes from 100 to 119. This was also received correctly. So the acknowledgement comes back. As far as the receiver is concerned, or B is concerned, it has received everything correctly till 119. It will send an acknowledgement saying, give me 120. Now at the sender side, it has not received the first acknowledgement, but it gets the second acknowledgement. The sender can still move along. It doesn't need the acknowledgement for the first packet to tell. It gets a subsequent acknowledgement which tells I have received everything correctly till 119. That's good enough. I don't need an acknowledgement for each and every packet. As long as you tell me how much you have received, that's how I will update my knowledge. Okay? So now it can send out a new piece of data starting at 120. Okay. This example was just to show that even though you may not get an acknowledgement for every single packet you sent, but from the numbers you get in any acknowledgement, you can still update your information on your side. All right. Now, having said that, now let's zoom into TCP's operation in a little bit more detail. And one thing you observe here is that two things, right? We send data, we get acknowledgements. And these acknowledgements are very important. They serve, to tell us how much data has been received, and the absence of an acknowledgement indicates loss of packets. So, if I think about it, I should think that every time I send a packet, I should get an acknowledgement back, right? Every packet should be acknowledged. But in real life, TCP doesn't exactly do that. It's a little bit different. So we do not send in an acknowledgement for every packet that is received. If I'm the receiver, I'm getting packets, I will not send an acknowledgement back in response to every packet. Why? The reason is, back in the old days, networks didn't have so much capacity. The bandwidth was limited. So if I sent out acknowledgements for every packet, then I was basically sending in these 40-byte packets into the network. They didn't really carry any data. So that was sort of loading the network a bit. So we wanted to avoid it. Okay? So maybe now our networks have enough capacity. Now every acknowledgement we can send easily. But maybe 30 years ago, this wasn't the case. So we tried to save on bandwidth. So let's see how we generate acknowledgements. There are 4 things here. So let's say at the receiver, we get a packet. This is something we were expecting. It's not out of order. Let's say I was expecting byte number 100, and this packet contains byte number 100. So the sequence number is in order, the way I was expecting. And so far, I have sent all the acknowledgements. In this case, what it says is, don't send the acknowledgement immediately. Wait for a bit. Okay. The basic idea is, rather than acknowledging every packet, I send one acknowledgement after I get 2 packets. 2 packets, 1 acknowledgement. That's basically what we're trying to do. So if I were to illustrate it here. Oh, this was on. I just need to shift this guy. So what it says is, let's say you got a packet. This is a new packet. This is in order. Don't send an acknowledgement yet. Let's say this started at taking our same thing, 92, and it had 8 bytes of data, right? So I'm going to wait. I'm not going to send any acknowledgement. When the second packet comes in, let's say this has sequence number 100, and it had 20 bytes. This is the time when I'm going to send an acknowledgement and say 120. Okay. What if there was a scenario where I sent the data and somehow the application doesn't give me any more packets, right? So let's say this was a new packet, sequence number is 120, and I don't remember, let's say 15 bytes of data. Now, at the receiver, what it says, so far everything that I have received has already been acknowledged. So I should wait. I should wait for a second packet to come in, and then I will send the acknowledgement. Good, wait. But now the application here doesn't have any more data to send. So the receiver is waiting. But now there's a timer associated with it, right? At some point, that timer will expire. So I will retransmit the data. And that'll be a waste. So what it says is, you can wait for a second packet to come in, but if it doesn't come in for some amount of time, and it's usually 500 milliseconds. I try to save bandwidth. I will try to wait for a second packet to come in and then only send a single acknowledgement for both packets. But I have waited 500 milliseconds already. No second packet is coming. I should not delay the acknowledgement anymore. In this case, even though I have only received one packet so far, I will still send an acknowledgement, 135. Okay. So this is what the first one says, If you get a new packet and everything has been acknowledged so far, delay the acknowledgement. You can wait up to 500 milliseconds for the next packet. If there's no packet coming, reply anyway. So this is what is delayed acknowledgement in TCP, and this is what most TCP deployments out there will use. Okay? And then the second line here, this guy, is basically saying you have received a packet, this is in order, everything is fine, and there's already one packet which you have not acknowledged. That means there's a second packet. In this case, you can send out a acknowledgement immediately. Right? So if it is the second packet, send out an acknowledgement. If it is the first packet, wait for the second packet to come in, or 500 milliseconds, you can send out. So that's the first two. And these are the scenarios where everything is going well. Sender is sending packets, you're receiving them in sequence. Now imagine a case where you do get a packet, but it is out of order. That means you are expecting, let's say, byte number 92. You don't get that packet with byte number 92. Instead, you get the packet with byte number 100, let's say, in our example. So it's an out of order packet. And an out of order packet, intuitively, it tells you that something is wrong in the network, right? I was expecting something I didn't get, but then I got something else. So now you can be a little bit suspicious and say, what happened to the previous packet? Has it been lost? Or maybe it took a different path, it's going to arrive, but maybe a little later. We don't know, but something has happened to that packet. In this case, we do not wait. We do not do any delayed acknowledgements. What we do is immediately send an acknowledgement. And this will be we do cumulative, right? So this will be a repeat of the acknowledgement for the previous packet. Also, if after a while you get a packet that fills the gap, means you were waiting for 92, you didn't get 92, you got 100, but after a while you got 92, which we're expecting. Again, this time you should not do delayed acknowledgement, you should send it out immediately. Okay? So let's see this in operation and why this is important, especially the bottom part. The bottom part is used for the second thing in TCP for detecting losses. Of course, we had timeout, right, previously. The second way TCP detects losses is through something called fast retransmit. And so when the first version of TCP came out, let's say in the 70s and so on, it only had timeout, that's it. And usually timer values are long. So you wait, and then you send. So that's not very efficient. So then the idea was, can I somehow detect a loss a little bit quicker? Okay? And that's where this fast retransmit comes in. Usually when you have a pipeline protocol, you're allowed to send multiple packets back to back, one after the other. Let's say one packet is lost, but the remaining packets make through. And if you get acknowledgements for those, then you may think that something is wrong, right? So let me give you an example of how this works. Let's say we have these hosts, and now I have a pretty large timeout value. Let's say I send a first packet, sequence number 92 has 8 bytes, right? The acknowledgement for this, let's say the packet was received correctly. The acknowledgement will say, oh, I got, starting from 92, I got 8 bytes. So 92, 99, I have received, give me 100. Let's say I had a window, and I'm allowed to send multiple packets. So immediately after this, I would have sent another packet, let's say, starting at 100, and it has 20 bytes. And then, but something happened in the network, we never received it. Let's say my window was big enough, I was allowed to send another packet. Now, even though the sequence number is not shown here, you can guess what the sequence number here would, oh crap. Too sensitive. Sequence number here would have been 120, right? Because the previous packet started at 100 and it had 20 bytes, so it would have gone up to 119. And then whatever data it had. And let's say my window was big enough, I was allowed to send a third packet and a fourth packet. And for each one of these, if you look at the receiver, what is happening? First got one packet with 8 bytes, so I said, give me 100. Then the actual packet with 100 never made it. But a packet with 120 made it. When the packet with 120 made it, at the receiver, this is out of order packet, right? So that satisfies this one. Arrival of an out of order packet. So when an arrival of an out of order packet, what happens? We send an acknowledgement immediately. And this would be a duplicate acknowledgement. Why is it a duplicate acknowledgement? Because TCP only does cumulative, right? I have received a new packet. It has a sequence number of 120. Maybe it has, let's say, 20 bytes of data. But what should the acknowledgement say? How far have I received correctly in sequence? That's still up to 99. I have only received up to 99 correctly. I have not received 100. So the acknowledgement for this will still say, I'm looking for 100. I have previously sent a packet acknowledgement that already says, give me 100. So this guy is duplicate. When the next packet comes in here, maybe the sequence number here, let's say, is, since I wrote 20 here, maybe it's 140. But the receiver is still looking for 100. Again, it's an out of sequence packet. So it will immediately send an acknowledgement, and the acknowledgement will say, how far have I received correctly so far? Till 99. So what am I looking for? 100. So the acknowledgement still says 100. This also is a duplicate, right? This is the second duplicate, actually. And now, when the third packet comes in, it also has some sequence number, depending upon how much data was there in the previous one. Let's say this is 150. Maybe the previous packet just had 10 bytes of data. But the receiver is still looking for 100. So it's an out of sequence packet. So I'm going to send an acknowledgement immediately, and it'll still say, give me 100. Now, if you think about it, at the sender side, at A, it says, all right, I sent packet with 92 that was received correctly. Then I sent many packets. Some of them were received correctly, right? Because that's the reason I'm getting this acknowledgement. First time I got the duplicate acknowledgement, I can think, oh, maybe my actual packet with 100 is taking a longer route, so it's going to take a little bit more time to reach. Then I get a second duplicate acknowledgement, which says something I sent after 100 has made its way, but 100 still hasn't made it. Is it still taking a longer route, or is it lost? We still don't know. Then I get a third duplicate acknowledgement, which again says another packet has made it to the destination, but 100 still hasn't made it. Now we can say at this point, since 3 of them have made it, most likely 100 is lost, it will never make it. So I can take this 3 duplicate acknowledgements as a sign that packet number 100 is lost. And then I don't have to wait for a timer to expire. I will retransmit that packet immediately. So this is what is called fast retransmit. When you get 3 duplicate acknowledgements for a packet, you assume that the previous packet must have been lost, and you retransmit immediately without having to wait for a timeout. Now you may say, Prof, why 3? Why not 4? Why not 2? Yeah. It's just very empirical. There's no science behind why it's 3. It's just something people felt comfortable with, I guess. That 3 seems like a reasonable number. 1 may be 2 less, right? And if I ask you to wait for 10, by the time most likely timer will expire anyway, that's probably too much. So it's just something people felt comfortable with, so we picked 3. Right. Now, this is sort of the details of what I was describing. The fast retransmit works like if you get 3 duplicate acknowledgements for the same data, you expect that the packet with the smallest sequence number so far has been lost, and then you can retransmit immediately. Later on, we will see that there are some, these real-life protocols are very, very complicated in the way that they will have some minor things here or there. So our goal is not to understand or to memorize every single detail. It's more about to understand the principle of how things are done. And in this case, that message is, you can wait for a timeout, but that can be inefficient in certain cases. So another way of guessing that a packet has been lost is if you get multiple duplicate acknowledgement, that gives you some information with a very high degree of confidence that most likely your packet has been lost. So no need to wait for a timeout. You can immediately retransmit. Questions? Yeah. Okay. So what happens is, so his question is, this is what happened. I got 3 duplicate acknowledgements. So that gave me so I took that as a sign that packet number 100 must be lost. So I retransmitted 100. So then the question is, immediately afterwards, should I resend, let's say, sequence 120? Should I do this? The answer is, we don't do it. Right? And the reason is, I know that I have received some duplicate acknowledgements. So data was going through. What has the receiver done with those 3 out-of-sequence packets? If it has thrown them away, then I would have to retransmit anyway later on. Sender doesn't know anything, right? So let's take an example of what could have happened here. Let me erase this last bit of thing. So let's say in this case, I sent 100, the retransmission, and let's say it has been received correctly. It's going to come back. I'm going to get an ACK immediately. No delayed ACK. Why? Because it's going to be in this category. Arrival of a segment that fills a gap. Right? Previously, I was expecting 100, 100, 100. It is filling that gap. So immediately send an ACK. What will that ACK say? The ACK here, now it depends what the ACK's acknowledgement number will be. What has B done with those 3 packets that had come earlier? It had 2 options. Even though they're out of sequence, it could have still stored them, or it could have thrown them away. If it had stored them, let's say, now the acknowledgement when it goes back, so this was 50, and let's say it had 10 bytes of data. This will say, give me 160. And when this acknowledgement is received, A knows everything till 160 has been received correctly. So no need to retransmit those. Let's say B's implementation was such that if I get an out-of-sequence packet, I'm going to throw it away. In that case, this would have said 120. Because the other 3 packets have thrown them away. So now it will move on to 120. In real life, most TCP implementations will keep out-of-sequence packets. The standard doesn't say anything. Your receiver, you get out of sequence. Should you keep? Should you not keep? You wrote the code. It's up to you. And most code, or if you look at any Ubuntu stack or Windows stack, keeps out of sequence packets. So in this case, you will not have to retransmit them. Yes, because when the acknowledgement comes back, it will be a cumulative acknowledgement. Anything it has stored till whatever gap it has filled, the acknowledgement will go back saying up to this has been received. So the sender will know what is the next one to send. Other questions? All right. Okay, so that was fast retransmit. So now let's look at some other features of TCP. One we've talked earlier is flow control. And flow control is to make sure that the sender doesn't send too much data beyond which the receiver cannot handle. Right? Earlier we had talked about congestion control and flow control. Congestion control is when the sender sends too much data that the links or the routers cannot handle. But let's say the links and the routers are okay. It's the receiver which cannot handle too much data. So then flow control comes in. So if you look at if you look at what's happening at a receiver, so again, we can look at the layers. At the very top, you have your application running. Then you have your transport. And then you have your network and other layers, right? So at the receiver, the physical layer will get the data, give it to the link layer, then give it to the network layer. Network layer will give it to the transport layer. Right? And then the transport layer is supposed to give this data up to the application. How? Through the socket. Right? So I'm TCP, I get data. I put those data in for the application to pick up through the socket. But the application will come when it's ready for the data, and then it'll take it. For the time being, what do I do with the data? I store it in the memory. And when the socket is created, what the operating system does is it also allocates some memory to that socket. So when I send data through that socket, I will write in the memory, and then the application process will come and read from that piece of memory. How much memory will be allocated to me? Depends on the operating system. A common value is about 4096 bytes in the old days, and that can vary. But the whole idea is that I have a buffer where I'm supposed to store the data, and then the application will come and read from this data, from this buffer. And if I'm an old machine, I don't have so much data, or my things are slow. If I'm a new, faster machine, maybe the memory is larger, and then the rate at which things will be read by the application will be higher. So what flow control tries to do is it tries to make sure that the sender doesn't send data at a rate higher than what my application and my memory can handle. So another way of doing this is you think of this memory like this. So this is the socket through which the application is reading the data, and this is the buffer that has been given to this particular port by the operating system. When I receive data, I will put in here. And at any point in time, there may be some buffered data. This is the data that the application needs to pull, and this is the free space. If there is no data that remains to be read, everything has been delivered to the application, then there won't be any buffered data, right? That's the whole idea. But at any time, there'll be some data that the application still needs to pull, and there's some free space. So let's say I have received some data. I'm the receiver. I received some data. I put it in the buffer. And now I'm going to send an acknowledgement back to the sender. In that acknowledgement packet, I'm supposed to do this flow control. So what I do is I check how much is this available. Maybe I have 2,000 bytes available. Right here, free buffer space is 2,000. So what I'll do is I will take this value of 2,000, and then if I go to my TCP packet structure, and you will see that there is a R receiver window field there. Here. I'm going to make this 2,000 and send it out. So when the sender gets this acknowledgement packet with 2,000 in RWND or receiver window, it says that don't send more than 2,000 bytes. Even though the pipeline, the N in the pipeline may allow you to send maybe 20,000 bytes, don't send more than 2,000 because the receiver cannot handle it. Okay? All right. So flow control was fairly straightforward. So now we'll move on to TCP connection establishment. So UDP is connectionless. So if the application gives UDP some data, it immediately directly sends it to the receiver. It doesn't care if the receiver is alive or currently shut down or whether it's willing to accept data or not. UDP doesn't care, but TCP cares. So before you can actually send the data, TCP will first check with this receiver whether it's willing to accept your data or not. So it will set up a connection. And just like you need to set up a connection at the beginning, once your transaction is done, you have transferred all the data that you wanted, you should also close down the connection. So there's a TCP teardown or TCP connection closing part also. So we'll look at both of them. So let's start with TCP connection establishment. And the connection establishment happens through a three-way process. We call it the three-way handshake. So whoever wants to start the TCP connection will first send a connection request packet. So what will that connection request packet be? All TCP packets follow the same format that we were just looking at, when I was doing RWND. It will have the same format, except some of the flags and some of the fields will be different. So when I first send a connection request packet, let's say A is sending, in the flag part of the packet, there is something called S in our thing, right? That's the SYN bit. So I will send a packet where this SYN bit will be set to 1. The flag SYN will be set to 1. SYN comes from synchronization. In the old times, we would think the sender and the receiver are synchronizing themselves. So this is basically saying, I want to open a connection with you. And when I say I want to open a connection with you, I also say that After this, I'll be sending you data. You should say the numbering of data should always start from 0 or from 1, and then go from 1, 2, 3, 4. Sequence numbers should go like that. It turns out that we don't always do that. One of them is because of security reasons. People may guess your sequence number and then send acknowledgements even though you may not have received. So there's some issues. So what we usually do is we start counting from some random point. So we pick a random value for our sequence number and then start our counting from there. So this is to say I want to open a connection with you, and my first byte will start at this. Just an offset in some sense. So if I go back to my data packet format, the SYN packet will only have, actually let's say there's no options, it will only have the first 5 rows. There is no data part in the SYN packet. And maybe there are no options also because they are usually not used. So the SYN packet only consists of this. And this S bit here will be set to 1. Whatever X value, that random sequence number that we have chosen, will be put in here. Of course, you have to put in your source port number and the destination port number. What should be the acknowledgement number value here? This is the first packet. I'm not acknowledging anything, right? So you can put whatever you want to put in there. It doesn't matter. All you need to do is this A bit here, which is for acknowledgement, you make it 0. So it tells the receiver that whatever I put in the acknowledgement number, it's garbage. It has no meaning. Okay? So your SYN packet will be 20 bytes from the TCP side. And the SYN bit will be set to 1. We'll put the sequence number. ACK will be 0. A bit will be 0. Okay? So I will stay on this because it takes me a lot of time to move from here to there, and maybe I'll just draw out that thing here. So I said SYN equals 1, and my initial sequence was X. So when the receiver gets this packet, it understands that somebody wants to establish a connection with me. Am I willing to accept? So basically it will check, do I have enough resources? Remember, for every connection that comes in, we have to set up a socket, then I have to allocate some memory for that buffer and so on. If I'm a server, maybe I already have 5,000 connections going on. Can I still accommodate this? Maybe you can. In that case, you will reply. And when you reply, the acknowledgement will be 1. That means you're acknowledging. And so this is let me put it this way. ACK bit. This is 1. And in the acknowledge ACK number, this will be X plus 1, signifying, yes, I have received your acknowledgement, I have received your SYN request, and I'm acknowledging. Please now give me X plus 1. Okay? So if I go back to this, this A bit is 1 now, and in the acknowledgement number field, I will put X plus 1. So when I do this, what happens is it tells this, let's say A, that I have accepted your request, you can send me data. But maybe B also wants to send data to A. So I have to open this direction of the connection. So in order to do that, I will also put the SYN bit to be 1. And this basically says, I also want to open a connection with you. And my sequence numbers will start at Y. So I acknowledge your part, and at the same time, I'm also asking to open my direction of the connection. So if I go to the same packet here, the SYN bit, I'm trying to circle S, that's also 1. And in the sequence number field, I will put Y. So the same packet will serve two purposes. It will acknowledge what I previously received, and it will also serve as a request for opening my direction of the connection. Okay. And now, once this packet comes here, as far as A is concerned, it knows that its request was accepted. But it also sees that the other side is requesting to open their direction of the connection. So I need to send an acknowledgement, and this time my ACK bit will be 1. Here, if you see your ACK bit, this was 0, and then ACK number will be Y plus 1, saying, yep, you wanted to start at Y, good, now give me Y plus 1. Okay. Another thing is, we always try to make things a bit more efficient. We don't want to waste resources. Let's say A also had some data to send at this point. You could say, oh, now you can send data in a separate packet. But it's not necessary. You are sending this acknowledgement for the other side. But at this point, your request for opening your direction of the connection has already been accepted, right? So this part is already active, data going from this side. You send a SYN, you got the acknowledgement. So you're allowed to send. So along with this acknowledgement packet, you can also add data to the same packet. Okay? So the third packet which goes out can also include data. And in this case, if I go back here, I can actually put data here. I'm going to put the ACK bit to be 1, and in the acknowledgement number, I will put Y plus 1. And since I'm putting data here, the first byte of the data I'm writing pretty badly. Let me do better than this. The first byte of this will start at X plus 1. So in the sequence number here, it will be X plus 1 if I want to add data. Right. So the whole point I'm trying to make is opening a connection is a 3-step process. You send a SYN, you get an acknowledgement. Along with the acknowledgement, you also get a SYN. Now you send a response acknowledgement for the third SYN, but with the third packet, if you have any data to send, you're allowed to send, because your connection has already been opened. Questions? Yeah. In the first part, because otherwise the receiver, it just basically says is, when I do the first packet, when I send the first packet, the connection is not open yet, right? But my packet will always have the acknowledgement number field. You can put all ones, all zeros, but whatever you put, it has no meaning because you're not really acknowledging anything from the other side. So it hasn't established anything, right? So there's no connection yet. But my packet has to have an acknowledgement number field anyway. Should I interpret that to be something? No. So I just say ACK bit is 0. So don't care about the acknowledgement number field right now. There's no connection. All right. So that was connection setup. So now maybe we'll go back to connection teardown. And connection teardown can be, it's usually a 4-step process. Let's look at it. So when I want to close a TCP connection, what I do is, just like in the flags, we had the SYN bit and the ACK bit, there's another flag there called F for FIN. Right? So I will put the FIN bit to be 1 to indicate that I want to close my connection. And whatever is the current sequence number I have consumed so far, I will put the sequence number X there. So this is basically telling the other side that I don't want to send any more data to you, I'm done. The other side, when it gets it, it will send an acknowledgement back saying, I acknowledge this. So it goes X plus 1, which is to say that I acknowledge your request for FIN. We are done. So at this point, when the acknowledgement is received, the sender knows I cannot send any more data. And the receiver knows no more data will be coming from that side. Or let me call it client and server. So after these two messages are exchanged, the client cannot send any more data. And the server is not expecting any more data from the client also. Can the server still send to the client? Yes, it can. We have only closed this direction of the data. The server is still allowed to send data. At some point, the server will say, I don't want to send any more data. And at that time, it will send a packet with FIN bit 1. And whatever is the sequence number at that point, Y. This is just to be, I'm sure you understand this, but this X and Y are not the same X and Y when we were setting up the connection, right? These will be different numbers now. Now, when the client receives this FIN request, it's supposed to send an acknowledgement. And the acknowledgement should increment by 1, Y plus 1, to say, I have received your FIN bit. At this point, we should not be expecting any more data from the server. So I can kill all my processes and done, right? Not done. We still wait for a specific amount of time. And the connection still stays open. And the reason is this. Yes, you have sent the acknowledgement for the FIN. What if this is lost? What if the network loses this? Then the server will think that the connection has not been closed. It will send the FIN request again. And if you have closed your shop and gone home, then you will not be there to respond, right? So you still stay open just for the event that maybe your acknowledgement is not received correctly. How long should this be? Different implementations do different things. It usually either half a second, 1 second, 2 seconds, something like that. Okay. All right, so that's TCP connection closure. Now let's come to the more interesting part where we will talk about TCP's congestion control. Right? And of course, we know why congestion happens. This is when senders send in data at a much higher rate, or at least the same rate or higher rate than what the network can handle. And as a result, the buffers in the routers start to fill up. And at some point, the buffers are completely full. And then you start experiencing packet losses. And also, if the buffers are full, your packets will be standing in line, waiting. So there'll be queuing delays, right? So we will have those. And as we mentioned, this is different from flow control. Flow control is the problem at the receiver. Receiver is too slow. Congestion control has to deal with links and routers. Right. And the way we see it is through packet losses and so on. And this still is, even after 20, 30 years of research, maybe more. Back when I was a student, it was one of the top 10 problems in computer networks, and many colleagues who worked on these things and so on, but it still is an important problem in data centers and things like that. So the whole idea is that, we want to avoid congestion. So I don't want to overwhelm the links or the routers. Let's say I'm connecting from here to a server, which is, let's say, in California. So in order to get to California, I have to pass through multiple links and multiple routers. Sitting here, especially as a regular consumer, I really don't know what the links are, how much bandwidth those links have. And the condition of those, even if I knew that there are these 10 different links and these are the capacities, I am sharing that with others. And the number of other people also on the network changes with time. Right now, if you look at the single link from here to the Wi-Fi access point, I don't know how many students, maybe 30 students are here. So 30 of us are sharing this. But after a while, maybe there are 20. Right? So that keeps changing dynamically. So the whole idea is that it is not known in advance what is the capacity of the network, because things are very dynamic and it can change over time. So the whole idea here is I want to probe the network. I want to test the network to see how much available capacity is, and then hopefully operate somewhere around there. So how do we do this? The way we will do it is, initially I will start very conservatively. Maybe I start with a window or n equals 1. I allow you to send only one packet. If that goes through and you get an acknowledgement, then you know, okay, I sent one, the network was able to handle. Maybe now I should send 2. So you increase your pipeline capacity or your n to 2. This time you send 2. Maybe you get 2 acknowledgements and everything is good. So you say, okay, network is capable of handling 2. What should I do? You have few options, right? You can say, oh, let me send 4 this time. I will double every time. If you get 4 acknowledgements back, so I sent 4, let's try 8 this time. If you get all 8 acknowledgements back, you can say I get 16 this time. So that's one option, right? You're doubling every time. Another option, maybe you started with 1, you got the acknowledgement, you go to 2, you get 2 acknowledgements. You say, I don't want to be too greedy. Let me go to 3. If I get 3 acknowledgements, then I'll go to 4. If I get 4 acknowledgements, I'll go to 5. And we will see TCP uses a combination of both of these. Sometimes it will do like exponential increase. Sometimes it will do a linear increase, right? So that's the increase part. Let's say I'm increasing. At some point, I will hit the capacity of the network. I cannot increase indefinitely or infinitely, right? Everything has a finite capacity. And when I reach that capacity, I will have a packet loss. So that should tell me that, oh, I have increased too much. That's not. So what should I do? I have caused congestion. I should decrease my rate. How much should I decrease? Let's say previously my window was 30. I can make it 29. That would be a decrease. Or I could go back to 1. That'll also be a decrease, a much bigger decrease. Or I could say, I was 30, let me go back to half. Maybe I'll start at 15 now. So there are all these different possibilities, right? And in general, in steady state, what we will see, the way TCP tries to operate is something called additive increase. That means I will increase linearly. I will send 3 packets if everything is good. Next time I'll send 4, next time I'll send 5, next time I'll send 6, and so on. So additive increase. Every time I add by 1. But if I experience a loss, I will not decrease by 1. I don't want to increase too quickly because that has a problem. But once there's a problem, I should try to address it very quickly. So problem means loss. I should address quickly. So I should not go from 30 to 29. That's a slow change. So if I want to address it very quickly, I should decrease much faster. So multiplicative decrease says, oh, you're 30, multiply by half, so you're 15, so do that. You don't have to multiply by half. You could multiply by, 1/3 or whatever. But in TCP, we usually do half. Okay? So this is how it would normally operate. When you are trying to probe for bandwidth, you will increase linearly. And once there's a loss, you will go back to half. Once you're at half, you don't stay there. You could say, now I have figured out where the loss is, let me stay there. But the idea is that at that point in time when you had a loss, the network could only handle this much. But network keeps changing with time. So you should always keep probing, and whenever you see a loss, you decrease. You don't stay static. That's TCP's philosophy. So next time you again keep probing, increasing linearly, maybe this time you were able to send more. But wherever loss happened, you decrease by half, and then this continues. Again, this is TCP's additive increase, multiplicative decrease process. Now, this is the general idea. But the way TCP operates, again, real-life protocols are more complicated than that. One of the views is, if I were to do this additive increase, which means linear increase, I will start at 1, right? I will start with sending 1 packet. When I start off the connection, the first thing I can try is sending 1. Then I will send 2. Then I will send 3. Most networks have good capacity, especially these days. So this will be very slow. So if you just send 1 packet and then acknowledgement, you remember what happened to stop and wait? You're basically doing stop and wait when it's 1 packet. So may not be very efficient. So what TCP says is, when you start off, let's do it quickly. But the name is very funny. It says slow start. But what we are doing is really the complete opposite. But slow start, the slow comes from, we start at 1. Okay? So when the TCP connection begins, let's say the handshake, the 3-way handshake is done. Now I'm allowed to send packets. I will start with 1 packet. Okay? And the way these things are kept track of, the window value and so on, TCP has its own terminology. Instead of saying n, the size of the window, TCP uses something called CWND, which stands for congestion window. So CWND is basically your size of your pipeline, how much you're allowed to send. And when we were doing go back n, selective repeat, we counted in terms of packets, right? 3 packets, 4 packets. But remember, TCP counts everything in bytes. So this CWND is also specified in bytes. So it will say, oh, currently the congestion window is 10,000 bytes. So you're allowed to send up to 10,000 bytes. Depending upon your packet size, if your packet size is 1,000 bytes, that means you're allowed to send 10 packets. Initially, the value of CWND, congestion window, will be the size of one packet. That's what this 1 MSS means. MSS is maximum segment size or maximum packet size. Right? That's basically one packet. Even though TCP counts in bytes and so on, for us, it's still easier to visualize or think in terms of packets, right? So we'll still do everything in terms of one packet, two packet. But remember that all calculations and all variables in TCP are maintained in units of bytes, not in units of packets. So initially, TCP is allowed to send one packet, congestion window. So slow start, you start with one packet or one segment. If it is received correctly, you get an acknowledgement back. And in slow start, every time you get an acknowledgement, you increase your congestion window by one packet or one MSS, whatever you want to think about. So here, initially, my congestion window was one packet size. In bytes, it could have been 1,000 bytes, but let's say in terms of packets. When I get this acknowledgement, I will add 1 to it. So right now, my congestion window or my pipeline size becomes 2. So I am allowed to send 2 packets. Let's say the network handles both of them go through. So I get 2 acknowledgements back. Of course, we had that discussion about delayed acknowledgements and so on. So we are not considering those things, but they will also be there. But this is just to illustrate what slow start is like. So when I get the first acknowledgement, my congestion window becomes 2 plus 1, right? Here it had become 2. When the first acknowledgement comes back, I increase my window by 1, so I'm allowed to send 3. And when the second acknowledgement comes back, I again increase by 1. So previously it was 3. So now it's 3 plus 1, 4. So now I'm allowed to send 4 packets. I send 4 packets. And then, if everything is good, I get 4 acknowledgements. Each one of them will increase my window by 1. So it will become 5, then the next ACK it becomes 6, then the next ACK becomes 7, the last ACK becomes 8. So my window is doubling essentially every round trip time. So each one of them is like 1 round trip time. So you can imagine that every round trip time my window increases by 2. Doubles. So this is TCP slow start, and the whole idea here is I want to ramp up very quickly. Now I can do this, so then it will be 16, then 32, then 64, 128, 256. But if I do this, I'm going to run into problem very soon, right? You can see that. So what TCP also says is we don't do this forever. There is also another variable. Where is it? I don't. Okay. There is another. Just like you maintain this, there is another thing called SS thresh, which stands for slow start threshold. And usually it will be something like 64, let's say, or 32, which says you can double. You go from 1 to 2, you go from 2 to 4, 4 to 8. This doubling only happens till your congestion window is less than this threshold. Once your congestion window hits this threshold, you cannot double anymore. You should increase linearly now. Right? And we will see how this slow start threshold also keeps changing with time. It's not constant all the time, and we will see that. All right. Now, how does TCP react to losses? In the case of a timeout, right? So TCP, as we saw previously, can detect losses in two ways. Either there's a timeout or there are 3 duplicate acknowledgements. In the case of a timeout, whatever your congestion window may be right now, it may be 3000, it may be 22, you will always decrease it back to 1. Right? You will decrease back to 1, and then you will go to slow start. How long will I continue? Till I hit the threshold, SS threshold. And then I will go linearly. Okay? However, your losses could also have been detected through 3 duplicate acknowledgements. In this case, you don't go back to 1. Whatever your window was, you just half it. And then you don't do slow start either. You just continue increasing linearly. Okay? And TCP, like any other protocol, has evolved over time. There are many different variations or versions of TCP. And in the 80s and 90s, these versions of TCP were not like version 1, version 2, version 3. Somehow the TCP community, they like to give them names. Right? Just like you have, I don't know, Androids. Android versions are named after those, ice cream or chocolate or something like that. In this case, TCP versions were named after, I don't know why, but cities or places in the state of Nevada in the US. So there's a TCP Vegas, TCP Tahoe, TCP Reno, and so on. So the oldest one was TCP Tahoe, and it said no matter what, we will always go down to 1. And this was not that efficient. So the subsequent version, which is TCP Reno actually, if it was 3 duplicate acknowledgements, you go down to half. So let me show that, how that works. All right, so let's consider this. A scenario, and the blue one is Tahoe, and the black one is Reno, right? But till this point, both of them work just the same, okay? So in this case, let's say the slow start threshold, I have kept it at 8 initially. Okay, let's say the initial value of slow start threshold is 8. And our connection, no matter which version of TCP, will always start with slow start. So I send one packet, everything is good, I get that acknowledgement, so now my window becomes 2. I send 2 packets, I receive 2 acknowledgements, window becomes 4. I send 4 packets, get 4 acknowledgements, congestion window becomes 8. Now my window has hit the threshold. No more slow start. Have to move on to congestion avoidance, which is linear increase now. So now I will send 8 packets. If all of them are received correctly, so actually the thing is like this. Previously, so let's say slow start. Every ACK plus 1, right? I would increase my congestion window by 1. In congestion avoidance, every ACK something like this. So what would happen is, if you get all of them back, if you send 10, you get 10 acknowledgements back, then your window will increase by 1. Okay? So this will give you something like a linear increase. But when we talk about, in class, we don't go into so much finer detail. We just show like this. If, let's say, you sent 8 packets, you got 8 acknowledgements back, next time you're allowed to send 9. You send 9 packets, you got 9 acknowledgements back, this time you're allowed to send 10. Then you're allowed to send 11. Then you're allowed to send 12. Okay? Let's say after sending these 12 packets, now you experience a loss. And in the case of, let's say, you detected it through 3 duplicate acknowledgements. Right? The loss was detected through 3 duplicate acknowledgements. In that case, in the case of TCP Reno, you will decrease your slow start. You will decrease your window from 12 divided by 2, which is 6. And in the case of Tahoe, you will go back to 1. And then Tahoe will do slow start. Reno will just do congestion avoidance, which is linear. Now, after I detect a loss, of course, depending upon whether it's, if it was timeout, both of them would have come down to 1. But if it is 3 duplicate acknowledgements, that's where the variation comes in. One will decrease to half and increase linearly. The other will decrease to 1 and do slow start. Another thing that happens is this value of SS thresh is also updated. Initially, this was at 8, right? When a loss is detected, SS thresh is updated, and SS thresh is set to half of the value of congestion window when the loss occurred. What was the loss? What was the congestion window when the loss occurred? It was 12. Half of that, 6. So SS thresh will now be updated to 6. So in the case of Tahoe now, I drop down to 1. Slow start is going on, so then it will be 2. Then it will be 4. And let's say I get back all 4 acknowledgements. The first one will increase by 1, so it will become 5. The next one will increase by 1, so it will become 6. But the next 2 will not increase by 1. So I will start my congestion avoidance phase at 6. Okay? And this is sort of the basic overview of the whole thing. And if you look at the actual details, it's a little bit more complicated than there are various other things. So for example, when you're in slow start, these are the things you do. Initially, you will start off with a window of 1. And let's say you pick some value for the slow start SS thresh. You also keep track of how many duplicate acknowledgements you have received so far. In slow start, if you get a new acknowledgement, you increase your congestion window by 1. If there's a duplicate acknowledgement, you keep track, so you can do fast retransmit. And in the case there is a timeout, you will drop down your window to 1, and your SS thresh will be half of the previous congestion window, and then you will just retransmit the missing segment. Whenever your congestion window becomes greater than slow start threshold, you enter the congestion avoidance phase. In congestion avoidance, every time you get a new acknowledgement, you don't increase by 1. you increase by 1 over congestion window. So you increase, if you get the whole window's worth of acknowledgements, you will increase your congestion window by 1. Basically, that's the idea. And if you get a duplicate acknowledgement, of course, you keep track of that. And of course, while you're at congestion avoidance, if there's a timeout, you will go down to 1 and you'll go back to slow start. The other thing that can happen is, let's say you're in congestion avoidance and you get 3 duplicate acknowledgements. In this case, what do? We retransmit the missing segment, we change our congestion window to half, we change our SS threshold to half the congestion window. And then there is this one funny thing here in this line. While you're retransmitting and waiting for new acknowledgements to come back, you're actually allowed to use the congestion window by 3. For every 3 duplicate acknowledgements that you got, you're actually allowed to increase by 3. And the reason for this is, we are just trying to squeeze out even a little bit of improvement we can. These are fine-tuning to some extreme, right? This was motivated by the fact that I got 3 duplicate acknowledgements. That means 3 packets were actually received by the receiver. I didn't increase my window for 3 duplicate acts. But maybe if I do, it's not such a bad idea because 3 packets have actually exited the network. So the network has capacity for 3 extra packets. So let's make use of that. So I will just increase them temporarily by 3. And then when I enter fast recovery, I will retransmit the packet. And if I still keep getting duplicate acknowledgements, I know that packets are exiting, so I will still keep increasing my window by 1. But as soon as a new acknowledgement is received, I say, okay, done. I can go back to congestion avoidance, and I will set my congestion window to slow SS thresh, which was done here. So this is the value of the congestion window when the previous loss occurred. Now this one takes a little bit of time, I know, to digest. What I will do is, there will be, I think over the break I uploaded some tutorial problems. When we do the tutorial problems, we will go through this in proper detail, and then hopefully you should be able to visualize what's going on. Questions? Okay, it's 35, so I think this is a good time for us to stop. So when we come back on Friday, we will get started on, network layer.